Right now, every single rocket that leaves Earth burns roughly $5 million of fuel just to reach orbit, and most of that rocket gets destroyed in the process, thrown away, never used again. And a Japanese construction company that built one of Tokyo's tallest towers looked at that number and asked a question that sounds absurd until you actually follow the engineering. What if you never launched a rocket at all? What if you simply built a cable 96,000 kilometers long from the surface of the ocean straight up into space and rode it instead? This is the plan Obayashi has actually put forward, with an actual target year, and by the end of this you'll understand why the entire multi-decade project comes down to a single material that, as of right now, does not yet exist at the scale this plan requires. No fuel, no explosion, no single-use hardware burned up and discarded on every trip. Just electricity and a cable strong, enough to hold a highway to orbit. The one thing standing between this concept and an actual construction site is carbon nanotube fiber, grown to lengths and strengths that have never been achieved before, and right now a sample of exactly that material is being tested in orbit aboard the International Space Station, because before anyone commits to building the tallest structure humanity has ever attempted, they need to know for certain that the one material holding the entire plan together can actually survive up there. Here is how they would build it, from the very first step. It starts, of all places, in a shipyard, where workers plasma. Cut 40mm steel plate into curved sections, each one bent to the precise radius needed to form a floating ring 400 meters across. The foundation of an ocean platform, built from 24 separate watertight compartments, each one welded completely shut before work even begins on. The next, and each one flood tested individually before it's allowed to leave the yard, because a single undetected leak here means an entire floating port eventually sinks. Section by section, the ring grows, every joint aligned to within 2 millimeters of its design position, underwater welders sealing the deepest joints at the base with welds that have to hold at sea for decades without failure. Inside every compartment, structural ring frames run every 2 meters, because a hull that flexes even slightly under load would eventually break the cable mount it's meant to support, and 48,000 tons of ballast concrete get poured into the base cells purely to stop this entire 400-meter ring from tipping in open water. From the inside, it genuinely feels like standing inside a submarine, which is essentially what it is, a sealed steel vessel engineered to survive the punishing equatorial ocean for the hull, powerful enough to steer this entire ring while it sits in open ocean, and the deck itself arrives in prefabricated sections, lowered into place, aligned, bolted, and welded flush with ballast lines running from the hull up to the control room, and every single valve and flange fitted by hand. Lightning conductors ring the full perimeter of the deck, because once this project is finished, the cable rising from its center will be the tallest object on the entire planet, and lightning will absolutely find it. Mooring chains alone weigh 6,000 tons combined, every link forged from high-strength alloy steel, and once the hull is finally complete, it leaves the shipyard for open water for the very first time, workers lining the deck as it moves. At the exact center of the ring, a terminal tower begins rising, 60 meters of steel lattice reaching straight up, power cables threaded through its legs, sensors mounted on every leg specifically to measure the smallest cable vibration from the very first second it's ever under load. A loading dock for the climbing vehicles takes shape around the tower base, built with guide rails and locking arms strong enough to receive a 100-ton vehicle docking directly at sea, because everything built on this platform exists for one single purpose: to grip a cable descending from orbit and never, under any circumstance, let go of it. And this floating port isn't just infrastructure, it's effectively a small city with a desalination plant, power generation, and full sewage. Treatment all being installed simultaneously. 6 separate generator sets fitted below deck, because a facility like this cannot be allowed to lose power, ever, under any conditions. Laser transmitter dish gets assembled on deck, which will eventually beam power upward to climbing vehicles as they ascend, while a cable entry seal gets fitted around the tower slot, specifically engineered to resist the kind of storm seas that will repeatedly try to flood that exact opening. Once the platform reaches its permanent station in the Pacific, thrusters fire, mooring chains draw tight, and workers simply watch the tension gauges and hold position. The ocean terminal is finally ready. Meanwhile, on land, the cable itself begins its life inside chemical vapor deposition reactors, growing carbon nanotube fiber one atom at a time, drawn continuously off the reactor onto a collection drum, required to be uniform, unbroken, and completely defect-free. Or the entire batch starts over from nothing. That fiber gets twisted, hundreds of individual strands combined and twisted together rather than simply bundled, specifically so the load shares evenly across every strand, and those twisted yarns get bound into ribbon form, heated rollers pressing a polymer matrix through the structure to give it its final shape. A protective coating goes over every surface of that ribbon, because without it, space radiation strips apart the carbon bonds within months, and every single section gets imaged under an electron microscope. Since even a tiny gap in that coating becomes a permanent gap in the ribbon's protection. The very first seed cable produced from all of this weighs only 20 tons, less than a single truck, and yet it has to hold more structural load than an entire skyscraper. That ribbon winds onto precision spools under carefully controlled tension, because a single kink anywhere in this material causes total failure the moment it's deployed, and each spool then gets sealed inside an inert gas transport canister, since raw oxygen exposure would degrade the ribbon over time. At the launch facility, every canister gets inspected on arrival before entering a clean room, mounted inside the spacecraft, its deployment mechanism cycled by hand repeatedly, every single release point tested before the vehicle is ever raised to vertical. The rocket takes on 300. Tons of liquid oxygen propellant, service arms retract, the pad clears, and ignition sends 20 tons of carbon nanotube ribbon rising on a column of fire destination geostationary orbit. Once in orbit, the spacecraft separates, thrusters fire to orient it correctly, and with 36,000 kilometers of open space stretching below it, the spool begins turning, feeding ribbon simultaneously downward toward Earth and upward toward a future counterweight. Ground crews track that. Descending ribbon on radar, a strand thinner than a single human hair falling across 40,000 kilometers of empty space, while at the ocean port, a capture crew stands at their stations through days of patient watching until the ribbon finally enters radar range. Below the cloud layer, and an aircraft snags it in midair, lowering it carefully down to the waiting deck. The moment that ribbon first touches the Earth port, workers manually thread it through tensioning drums, one guide roller at a time, until tension finally locks it. Taut across an unbroken span from the surface of the Pacific Ocean all the way to geostationary orbit. A single continuous structure, and by any measure, the longest object humans have ever built, put in place, using just one rocket launch. Once anchored to the drum clamps and torqued down bolt by bolt, a weather enclosure seals around the ribbon's entry point because salt spray alone is enough to destroy carbon nanotube fiber over time, and monitoring instruments on the anchorage are sensitive enough that if tension shifts by even 1%, the control room knows immediately. With the seed cable finally stable, the real challenge begins, because a 20-ton ribbon isn't nearly strong enough yet to carry real cargo. It has to grow. Back in Japan, climbing vehicles are built from heavy steel chassis welded up in dedicated assembly jigs, magnetic linear motor units bolted onto their arms, specifically to grip the ribbon and drive the climb upward. Gripper rollers fitted and hand-checked individually on every side. Laser receiver panels mount to the underside of each climber, since power for the entire climb comes from a beam sent up from the Earth port itself, with no fuel and no batteries required, while thermal blankets cover every exposed surface because a single trip from sea level to orbit puts each climber through a temperature swing of roughly 400 degrees. Every climber also carries a repair dispenser that bonds fresh reinforcement. Ribbon onto the cable as it rises, cargo lock jaws on the deck strong enough to hold a 100-ton payload, steady for up to 7 days, and emergency brakes on every gripper arm that clamp down instantly the moment power fails, ensuring the climber simply stops rather than falling. After a full electrical bench test with every drive energized and every sensor confirmed clear of faults, the very first climber gets loaded for sea transport, a 3-week journey to the equatorial port, where a crane finally swings it across from a supply ship and guide rails catch it home. Workers thread the ribbon through this climber's slot. The grippers close, the laser locks onto its receiver panels, motor drives spin up, and the very first climber begins to rise. Slowly at first, then steady, the ribbon holding firm under its first real load. From that point forward, cable production factories run around the clock, 510 separate reinforcements. Climbers scheduled for loading, each one carrying a full spool of reinforcement ribbon, bonding new material onto the growing cable layer by layer as it ascends, while the control room tracks every single climber's altitude and bond quality in real time. And if any bond comes back weak, that climber simply stops and redoes the section on the spot, rather than continuing upward with a flaw built in. Returned climbers get serviced at the dock, worn rollers swapped, inspection sensors recalibrated and sent straight back onto the ribbon. When satellites cross the cable's path, port thrusters fire to swing the entire ribbon briefly clear before returning it to station, and ground crews physically inspect the lower sections by contact trolley after every storm, replacing lightning ground straps whenever needed, treating each strike as a routine consumable event rather than a catastrophe. By the time the 100th climber is loaded, the ribbon at the tower guide has already doubled in diameter from where it started, damping masses clamped at. Calculated intervals along its length specifically to prevent resonance once multiple climbers are running simultaneously. Around year 6, factories retool entirely for wider ribbon production. because the cable has finally grown strong enough to support the heavier spools that follow. By the time roughly 300 climbers have flown, workers are already swapping in wider bore guide rollers because the cable has quite literally outgrown its own terminal hardware. By year 14, factories are producing the cable's final target thickness, and by year 15, the very first real cargo, not reinforcement ribbon, but actual station components, begins riding the cable upward, proven by a full load test. Carrying 100 tons, while terminal load cells confirm the structure sits comfortably within its design limits. While climbers continue reinforcing the cable, an entirely separate construction effort builds a station at geostationary orbit, module by module, each one launched to orbit by rocket. An irony. Nobody working on the project has missed. Rockets are what build the very thing designed to eventually replace them. Modules dock and latch together in orbit one at a time, confirmed from the port control room below, while a rotating gravity ring, assembled on Earth in segments, gets built to spin once installed, simulating something close to Martian gravity for the crew living aboard it. Solar array trusses, hinged and pre-assembled on the ground, unfold automatically once in orbit, while construction climbers hold steady positions along the cable, so robotic arms can reach out and bolt frame sections together piece by piece. Workers themselves eventually climb all the way to geostationary orbit by cable, fitting internal life support systems by hand in microgravity across 8-day shifts, cable guide bearings threaded through every level of the station. Specifically engineered, so the ribbon itself passes cleanly through without ever touching the surrounding structure. Once solar arrays deploy panel by panel and the station stands complete, docking ports open for the first time, and workers realize they've quietly built an entire functioning city at 36,000 kilometers above the Earth. The very first crew rides the cable back down from that station, 8 days up, 8 days down, the first of what will eventually become thousands of similar trips. Above the station, a massive counterweight, 12,500 tons in total, gets assembled on Earth in blocks and loaded onto cargo. Climbers one module at a time, each one weighed and logged precisely at the dock before departure, attached progressively farther out along the cable until it finally reaches the full 96,000 kilometer design length, tension at the terminal rising steadily as that counterweight. Mass grows, monitored kilopascal by kilopascal from the control room. Only once all of that is proven does the first passenger climber get fitted out, seats, full life support, viewports installed panel by panel, and put through complete boarding rehearsals at the dock until loading runs as fast and safely as boarding any ship. Life support consumables get loaded and inventoried item by item for a full 8-day climb. Every gripper alignment, power system, and communications link checked one final time before the hatch closes for the very first passenger flight. Day 1 passes through the atmosphere. Day 3 crosses the Van Allen radiation belts. By day 8, the climber reaches geostationary orbit, every meter of that ascent tracked continuously from the ground. Power beam holding steady, cabin pressure stable, every reading nominal the entire way. At the station, the crew waits at the docking hatch as the climber finally appears below after 8 full days, a docking arm reaching out to receive it, latches engaging, hatch seal confirmed. And for the very first time, a human being steps directly from a cable into a space station, having never once ridden a rocket to get there. From that point forward, the Earthport stops being a construction site and simply becomes a working terminal. The ocean platform, the station at geostationary orbit, and the counterweight far above, all functioning together as one integrated transportation system, with satellites riding to orbit on the cable itself. No rocket, no flame, no noise at all. The stated cost comparison behind this entire plan is roughly $10 per kilogram to orbit, against roughly $2,700 per kilogram using conventional rockets today. A difference large enough that a second port and a second cable are already part of the long-term plan, because in this vision, a single ribbon was never going to be enough. All of this, on paper right now, is a proposal with a stated 2050 target, not a completed structure, built in the plan by welders, climber mechanics, ribbon technicians, and control room crews, one bolt tightened at a time, 96,000 kilometers from the surface of the ocean to the far end of a counterweight in deep space, using the same basic tools and the same human hands that build almost everything else on Earth. None of it exists yet, but the material at the very center of the entire plan is being tested in orbit right now, and if it holds, the rest, according to the people proposing it, is simply engineering.